All right, welcome here to section 8.4 for algebra. This is scientific notation. When we talk about scientific notation, important emphasis I would like to make here is that scientific notation was created so that we could write really big numbers without having to put all the digits in there. So if we were talking about the number of miles it is from the Earth to the Sun, very, very large number. To put all those digits in there, it would be a lot. If we also want to talk about really, really small numbers, we want to start talking about the weights of protons, neutrons, electrons. We're talking about things that are 10 times 10 to the negative, 10, negative 17th power. Very, very like minuscule, very microscopic type thing. So scientific notation was created so that we could write really big numbers or really small numbers without having to put all the digits in there. I want to emphasize right here that a scientific notation, I'm going to highlight it as we go, is a number written such that it is in the form of c times 10 to the nth power. Well, what I want to emphasize here is this c. This c is defined right here as having to be a number that's between 1 and 10. When we talk about it being a number between 1 and 10, we're talking about something that could be equal to 1, but has to be less than 10. So what that means is that we're going to be allowed to have one digit left of the decimal place. We'll go through some examples in a second. And then the second part of it, it says that the exponent n has to be an integer. If x is going to be if n is going to be an integer, that exponent, an integer is a positive and negative whole number. So some examples in scientific notation are up here at the top. The first one is 2.13 times 10 to the 4th, or 5.001 times 10 to the 12th, or 7.897 times 10 to the negative 3, or 8.003 times 10 to the negative 7. The key thing here is we want to understand that there is only one digit, having to be a 1 through a 9, that is the left of the decimal place. We cannot have a 0 in front of left of the decimal place, so we can't have 0 point something, and we couldn't have like 22 point something, because that would be then putting two digits over here, and we already emphasized that this m, or this c value, has to be a number between 1 and 10. I'm going to give you the word of the day, and that is called a mantissa. So this number we're talking about here is a mantissa, so you can bring that up at your dinner conversations. I also would like to emphasize that as we take a look at multiplying by 10 to the first, or multiplying by 10 to the second, or 10 to the third, as I look at this here, multiplying by those numbers is going to make it larger. What I mean by that is that multiplying by 10 to the first would be the same as multiplying by 10. Multiplying by 10 to the second is the same as multiplying by 100. Multiplying by 10 to the third is multiplying by 1,000, which is why those numbers are going to be becoming larger when we look at that. I also want to look at those negative exponents. So if I have 10 to the negative 1 power, that's equivalent to multiplying by 1 over 10 to the first, or multiplying by 1/10. Multiplying by a tenth would also be the same as dividing by 10, or multiplying by 10 to the negative 2 would be equivalent to multiplying by 1 over 100. So 1/100th is what we're looking at here. Or 10 to the negative 3 is multiplying by 1 over 1,000. So you're talking about 1/1000th of it. So let's get into some problems here. First group of problems is asking us to rewrite in decimal form. Well, what I'd like to remind you here is that if I'm going to multiply by 10 to the second, this is a positive exponent, and I know that a positive exponent is going to make my number larger. The reason it's going to become larger is because we're multiplying by 10 squared, which is the same as multiplying by 100. So I'm going to be moving this decimal place twice to make it larger. Well, to make it larger, we move the decimal place 2 times, and we end up with that larger number, which is 283.4. Again, we take a look here. We're going to be dealing with a positive exponent, which is going to make this number here larger. So I'm going to be moving the decimal place once to get on the other side of the 9, and then I'm going to have to move it 1, 2, 3, 4 more times. So I'm adding 4 zeros after that 9. This number is 490,000. Let's be careful here. We're multiplying by a negative exponent, or times 10 to a negative exponent. which is going to make my number smaller. So if I would like to make it smaller, I'm going to move the decimal place once to get it on the other side of the 1, and then I need to move it 1, 2, 3, 4, 5 more times. So I'm going to have to add in 5 zeros to make that number smaller. Again, recognize here that multiplying by 10 to the negative 6 is multiplying by 1 over a million. So that is why this is becoming such a small number. All right, let's prepare for ourselves as we look in problem 4, 5, and 6. Now the directions are going to flip us around, and they're going to ask us to write in scientific notation. So I'm going to realize here that we're dealing with a number that is greater than 10. So that means that I'm going to be dealing with a positive exponent. So as I take a look at this, I know that it's going to be times 10 to a positive power. If I take the decimal place from, right now it's on the back side of that 0, I'm going to have to move it all the way over here so that I get or create what we talk about as that number between 1 and 10. So 3.469, and we need to count how many places we moved it. That would be 1, 2, 3, 4 places. So in scientific notation, this is 3.469 times 10 to the 4th. If I look at this problem, again, it is a number that is greater than 10. So we're dealing with a positive exponent. Those will be mental notes that you'll be making as we do more of these problems. And we're taking the decimal place and moving it from after the 0 in between the 1 and the 7. If I count how many times I move this, 1, 2, 3, 4, 5, that would be 6 times. If I take a look at problem number 6 is a number that is smaller than 1. Since it's a number that's smaller than 1, we're going to end up here with a negative exponent. And if I'm going to end up with a negative exponent, again, we are going to need to count how many times we're going to have to move this from going from here in between the 9 and the 3. That 9 and the 3, 9.3 would be our number between 1 and 10, and the decimal place is going to move 1, 2, so this is times 10 to the negative 2. All right, what happens when we start computing some of these without a calculator? Well, we know that we are allowed to multiply numbers. We have covered exponents. But one thing I want to talk about is this idea of the commutative property. And what the commutative property says is that we can change around the order in which we write something. And the reason I'm going to do this here is because we understand that 2 times 4 are two numbers that can be multiplied together to give us 8. We also realize that we have here 10 to the 4th and 10 to the negative 8th. Well, those are in fact the same base. So if those are the same base, I can add these exponents. And I'm going to end up with 8 times 10 to the negative 4th power. Nice and easy. Likewise, we can do similar type of things here. It may be beneficial for us to write this problem with a division bar as opposed to with a division sign. And if I took this here and did 1 divided by 2, I know that 1 divided by 2 is 1/2 or 0.5 as a decimal. If I take a look at 10 to the 9th and 10 to the 8th, using my exponent rules, I can subtract those. I feel like I made a really good start here. The one thing I want to remind you here is that we have to be careful of is 0.5 is not written as a number that is having 1 digit left of the decimal. So if I wanted to adjust that, I'm going to have to change it to 5.0 times 10 to the negative 1. The reason it's 10 to the negative 1 is because this number started out small, and I'm moving it 1 time to get it over there. I still have in this problem the times 10 to the 1st here. If I combine these bases of 10 and add those exponents, I would end up with 10 to the 0. And if you would like, you could write it like that, or the final answer here would just be 5. In problem number 9, I have two items being multiplied together inside the parenthesis. This is called a power of a product. What I need to do is I need to share that exponent with both of these. So I get 4 to the third multiplied by 10 to the negative 2 to the third. We're going to multiply those exponents and get 10 to the negative 6. Using my power sheet, or my memory, 4 to the third is 64 times 10 to the negative 6. Again, we'd like to be careful. 64 is not written in terms of scientific notation. That is a number that is larger, so when I rewrite this, this is going to be 6.4 times 10 to the first. Like we said before, we still have the 10 to the negative 6 on the back end, so we can leave this 6.4, and when we add up those exponents here, this is going to be times 10 to the, this will be the negative fifth. And again, the emphasis is when something starts in scientific notation, we write our answer at the end in scientific notation. Let's move to page 2. When we look at page 2, we get into how to compute using our calculator. So I'm going to take a look here at this problem. If we use parentheses, we will be in good shape. You could type in 3.69 times 10 to the negative 9th, close those parentheses, hit the division sign, divide by 8.2 times 10 to the negative, 10 to the 12th, and close those parentheses. You may also, please be aware of this here, is that you may also, for scientific notation, press the second button and the comma. What this will do is when you write this, it will write it as 3.69 E negative 9. And what that E stands for is that's an abbreviated way to write scientific notation in the calculator. The idea of this here is it uses less characters. By using less characters, we are allowed to write more on the calculator. I'm going to hit enter, and I'm going to write down that the calculator tells me that I get 4.5 E negative 22. Well, I would like to rewrite this because if it starts in scientific notation, we want to write our final answer in scientific notation, and that is 4.2 times 10 to the negative 22. Let's try two more problems like this. In number 15, type it in your calculator, 5.278 times 10 raised to the negative 9. Important that you keep these in parentheses. You could also use that second and the E button if you don't want to do times 10 to a power. And then from here, we're going to write 2.396 times 10 to the 27th. Remember, this here means approximately. We get 1.264 6088 E19. Well, I'm going to take this and round this to the nearest, let's say the nearest hundredths place. So here's a hundredths place. I'm going to look at that 4. That 4 is smaller than 5. So we can truncate or drop off the back end of this. And this is times 10 to the 19. Again, I would like to emphasize that this is approximately. It's not exactly this because I did do some rounding. Please make sure that in problem 16 that you do in fact use the parentheses. This is 4.76 times 10 to the 14th. Again, you can use the second and the comma button and do the E14. And then we raise that to the negative 6 power. When we raise to the negative 6 power, please recognize that this is going to be the caret symbol, negative 6. As I do this, again, we're going to end up with 8.59722 keeps going on, E negative 89. Again, I'm going to stay consistent with my rounding rules. I'm going to look at the third decimal place. which is a 7, which means I'm going to round up. But when I round a 9 up, this is a 5-9. That 5-9 is going to round up to be a 6-0. And we get the answer here is approximately 8.60 times 10 to the negative 89. All right, the last problem here, we can read it, and I'm going to write some notes here at the bottom. But we got the Louisiana Purchase from 1803 was purchasing 8.28 times 10 to the 5th square miles. A square mile would be a mile by a mile. So it's a mile going north and south, a mile going east and west. Very large area of land in the United States. And the cost of this was $15 million. 50 years later, so the U.S. decided they wanted more land. So in 1853, they made what was known as the Gadsden Purchase. The Gadsden Purchase was, I believe, what we think of the land area, Arizona, New Mexico, that area. And that was a purchasing 2.94 times 10 to the 4th square miles, and this cost was $10 million. What they would like us to do is to find the average cost of each property. So the average cost per square mile. So how do we find an average cost? To find that average cost, we are going to do the cost divided by the land area. And that will give us the average cost per 1 square mile. So let's take a look at this first one here. Louisiana Purchase was costing $15 million. $15 million is 15 times 10 to the 6th. Amount of land we purchased here was 8.28 times 10 to the 5th. I can grab my calculator. As I do 15 times 10 to the 6, I do want to make sure that I keep this in parentheses. And likewise, when I do the denominator, I would also like to make sure I put this in parentheses. The reason for that is because you're dividing one scientific number by another scientific notation number, not just apportion it. So as I hit enter my calculator, I find out that this is going to be, I would not like to say equals, I'm going to make sure that we are appropriate here. And this is approximately 18.11594203. I can say that this is American money, so we're going to round it to, looking at the third decimal place that is a 5, I'm going to say it's about $18.12 per 1 square mile. All right, let's look at the Gadsden Purchase. A little bit smaller area land. And let's find the average cost here. As we work to find the average cost, again, the average cost is going to be the cost of the land divided by the amount of land we had. So again, this is $10 million. So this is 10 million. 10 million is 10 times 10 to the 6 divided by 2.94 times 10 to the 4th. When we utilize the calculator, we do need to make sure that we're using parentheses here. And if you give me a moment, I will type this in my calculator. And we'll see what we get. Question is, as we're getting ready to compute this, do you think this is going to be cheaper purchase because it was less land and less money? Or do you think it's going to be more expensive? And the correct answer here is more expensive. So this here is giving us an average cost of, again, we're going to round it 2 decimal places for American money. 0.136 will round up to be 0.14. So that's $340.14 per 1 square mile. Well, as history will come to show, and could be debated, which purchase was better? Which was a better deal? well, a lot of that lies in maybe what was of value within that land. It also has to be noted that this is looking at 50-year time period, so there's a thing called inflation. So really the dollar in 1803 was probably worth a lot more than the dollar was worth in 1853. But again, this just gives you an idea of how to use scientific notation as we're looking at finding the average cost of some very large land areas that were costing in the millions of dollars. So that is a wrap here, and welcome to scientific notation. Very, very useful, not only in math, but also in the world of science.